Okay, so welcome to the next lecture. This one is relevant only for those students attending the V3B version of the lecture, so the one for bachelor students and for mathematics master students. And what's the topic today? The topic is, well, you can stay here. So, it's highly relevant for everyone, but in the exam, this will only occur in the part of the exam for the V3B students. But okay, I shouldn't have said this at the beginning. I should have said this at the end. Okay, so what's the topic today? So the topic is we defined the semantics of simple Haskell programs in the last lecture. And simple Haskell programs are pretty restricted because, well, essentially they have no pattern matching. And so the question is, how can we extend this to complex Haskell? So that's the goal today. So we will introduce an automatic transformation. An automatic transformation from complex to simple Haskell. And, well, what's the difference between complex and simple Haskell? The most important difference is here you may have pattern matching, so you may have several equations defining a function using pattern matching, and here you may not have pattern matching. So the question is how to get rid of this. And the solution is we introduce a certain set of predefined functions. And these predefined functions, they depend on the data structures that you have in your Haskell program. And we started with that already in the last lecture. So for this, we extend the set of predefined functions and, well, how do we extend this? Well, we extend it by a function bot. And, well, this function bot, we could define this ourselves in simple Haskell, but since we use it so often, we predefine it. And what is the semantics of bot? Well, the semantics of bot is it should always be undefined. So bot has an arbitrary type A, and it is always undefined. So if you define this yourselves, you could define it by this equation, bot equals bot. Now, what else do we define? We define a function is a construct for every data constructor construct. For every data constructor. And what's the idea here? Well, if you have pattern matching, then you can use pattern matching to find out whether some object is built with a certain data constructor or not. And since we have no pattern matching anymore in simple Haskell, we need some other way of finding this out. And therefore, for every data constructor, we use a predefined recognizer function which recognizes this data constructor. So what's the type? Well, if you have a data constructor construct, and the type of construct is the following one. So it's a constructor of arity n, and it takes arguments of type 1, type 2 to type n, and then gives you back something of the new type here. Then is a construct takes something of this type and returns true or false depending on whether the object is built with this constructor or not. So for example, how would this look like, for example, for lists? So if we have the data structure for lists, so data structure list A with two constructors nil and cons, where cons has two arguments of type A and of type list A. Here we would have two is a functions, a function is a nil, and a function is a cons. Is a nil returns true only for the argument nil, and otherwise it returns false. And similarly, is a cons returns true only if the argument is built with this data constructor, and otherwise it returns false. So if you want to define this yourself in full Haskell, of course, it's no problem to define this, but in simple Haskell, this would be a problem. So for example, is a cons would be a function which takes a list object, gives you back a Boolean, and, well, it just checks whether the argument is built with cons. And if it is built with cons, it returns true. And if it is built with nil, it returns false. Now, what else do we need? If we have pattern matching, we can, yes?
But isn't this not simple Haskell?
This is not simple Haskell. So, in complex Haskell, it could be defined like this. In simple Haskell, it cannot be defined. And therefore, in simple Haskell, we take it to be predefined. This is just the illustration, what should is-a-cons do. So we cannot define it like that. It's just to show to you what should it do, what should be its semantics. So in complex Haskell, we could define it like this. Like this. In simple Haskell, we can't do this. So in simple Haskell, we add this function is-a-cons to the predefined functions. Because we cannot define it ourselves. And now, what is pattern matching good for? Well, one thing that pattern matching can do is something like this. It can find out whether your argument is built with this constructor or with this constructor. And the other thing that pattern matching can do is it can extract the arguments of a constructor. So it can extract this first argument and it can extract this second argument. And so for this argument extraction, we need another predefined function, namely an arg of function. So for every data constructor, we also introduce this arg of function. And what it does is it takes an argument of a type. And if this is built with this data constructor, then it gives you back the tuple of the arguments. So how would it look like for the data constructor cons? So arg of constru for every data constructor constru. So how, in simple Haskell, again, we cannot define it. In full Haskell, we could define it. And if we had full Haskell, we could write it, for example, like this. So for the data constructor cons of the data structure for lists, it would look like this. It would take a list and return the tuple of its arguments. And cons is a constructor of arity 2, so it has two arguments. So it should return a tuple where the first argument has type A and the second has the type list A. So it should return a tuple of something of type A and something of type list A. And well, if we had pattern matching, then we could define this ourselves. So if this is applied to something of this form, cons xy, it should return the tuple consisting of x and y. And this is essentially what pattern matching is good for. It can find out with which constructor some object is built, and it can extract the arguments. And it can do this not only for objects built with data constructors, but it can also do the same thing with tuples. It can find out whether something is really a tuple or not, and it can extract components from tuples. And therefore, we need these is-a and arg of functions also for tuples. So we need a function is a n tuple, is a n tuple for all n 0, 1, no, well, not for 1, 0, 2, 3, and so on. And how do they look like? Well, we don't want to have infinite, yes? Yes?
What happens if I apply Arg to a constructor with no arguments?
Well, arc of nil, for example, would look like this. Arc of nil would also go from list A, and the result would be a tuple of the arguments of nil. Well, nil has arity 0, so the result would be a tuple with 0 components, and it would be defined like this. Arc of nil, if you apply this to nil, you get the empty tuple. Oh yes, you might say this makes not much sense, and yeah, you can do without, but why make an extra case for constructors with 0 arguments? It works also in this way. Okay, now we need similar functions, is and arc of also for tuples, and the set of predefined functions should be finite. So we don't want to do this for arbitrary large tuples, but it will turn out that when we transform one complex Haskell program into a simple Haskell program, we can find some upper limit, and we will only have tuples which are not greater than a certain upper limit which we can deduce from the program. So it will be sufficient to consider tuples only up to some number k, and this number k depends on, so k depends on the original complex Haskell program. The original complex Haskell program. So what does this do? Well, it works like this. So is a n tuple would take an arbitrary tuple with n components, so of the type tuple, where the first component has type a1 and the last component has type an, and it returns a Boolean. And well, whenever this is really applied to n components, then it returns true. But if it is applied to bot, for example, then it's not terminating. Then it is then it gives you bot. So this does not always return true, but if I apply is a n tuple to bot, then this is undefined. So this would not terminate, because bot, to evaluate this, I have to evaluate bot, and if I start evaluating bot, then that's the end. And okay, we need not only an is a function, but also an arg of function for tuples, when that works like the arg of function above. So we also have this arg of n tuple function. No, sorry, we don't call this arg of. And we need something similar like the arg of function. Namely, if we have a tuple with n components, we need a selection function to select the first component from the tuple, or the second component from the tuple, or the last component from the tuple. So what we need is we need these selection functions. And for every tuple with n components, we must be able to select the first argument, or the second argument, or the nth argument. So we need these functions cell ni for all n, and these n are the sizes of the tuple, and for all I between 1 and n. And the idea is this should select the ith component from a tuple with n components. So this selects the ith component from an n tuple, so a tuple with n components. So for example, let's make one example, cell 3,2. Cell 3,2 would select the second component from a tuple with 3 arguments, and if you have pattern matching, then it's not difficult to program this. So this takes an arbitrary tuple with 3 components, and it selects component number 2. So component number 2 has the type A2. And how would this work? Well, if you give it the arguments x1, x2, and x3, then it gives you back x2. And so with pattern matching, you can write this And without pattern matching, that's going to be a problem. Yes? Well, for n, if n is 0, then you can have this function for all I between 1 and 0, and there is no I between 1 and 0, so it makes no sense. But it's not wrong if I write it like that. So indeed, if n is 0, there's no selection function. But as soon as n is 2, there are already 2 selection functions, because you can select first or second component. So indeed, yes. So if you want, I can also remove this, and that doesn't change anything. Okay. You're right. Okay, so these are the predefined functions. So I have them also on the slides over here. Yeah, indeed, on the slide I also decided to start with n greater or equal to 2, so this was a good remark. So let's define this formally. So here's definition 228 on the new predefined functions. Okay, so for a Haskell program, with the data constructors con, the following functions, namely the functions on the slide, are considered to be predefined. The functions bot is a constructor, arg of constructor is a n-tuple, and cell and I. So the functions above are considered to be predefined. And what is k? So k is the largest size of a tuple that I will need when I transform this Haskell program into a simple Haskell program. And it turns out that it's sufficient to consider tuples of the following size. K is the maximum of the following things. The arities of the function in the program. So if you have a function of arity 3, then k must be at least 3. And if you have functions that take lots of arguments, 5, then, well, k has to be at least 5. So of the arities of the functions in the program, the length of the tuples in the program, and the number of declarations in the program. So clearly k is a finite number. So that's the essential message. It suffices to add these finitely many predefined functions, and they only depend on the original program. They only depend on the constructors that I have, and, well, on this number k, which also depends on the original program. So, in other words, we do not need tuples with more than k components in the transformed simple program with more than k components. And since these functions now are predefined, of course, when we discuss about the semantics, their semantics has to be predefined as well. So well, how do we know the semantics of predefined functions? Well, there's an initial environment, which we denoted by small omega. And this initial environment tells us what the predefined functions mean. And now we have some additional predefined functions. So the initial environment also has to tell us what these predefined functions, these additional predefined functions, mean. So the initial environment omega, is extended to an initial environment omega tr for transformation as follows. And well, what we do is we assign the intended semantics to these additional predefined functions. So what's the desired semantics for this new function bot? Well, it's bottom. And what's the semantics for is a constr? For is a constr? Well, the semantics is a function which operates on the big domain, on this big set DOM. So it takes some element from the domain, and then it checks whether this element is built with this constructor. And if so, then the result is true. So this function returns true. And it's the version of true which is labeled by the set that it comes from. So it's labeled by that it comes from constructions 0 in DOM. If this D really starts with this constructor. So if D starts with this constructor, constr, applied to certain arguments, D1 to Dn, in constructions N in DOM. And if this is built with a different constructor than this one, then it returns false. So it returns false in construction 0 in DOM if D starts with some other constructor, constr prime, D1 to Dm, in constructions M in DOM. M in DOM. And otherwise, the result is bottom. So this Haskell implementation, this was just to illustrate the semantics. The real definition of is a constr is this one. We say that the initial environment maps this function symbol to this function. And this has to be fixed in advance, and then afterwards we can translate any complex Haskell program into a simple Haskell program. Okay, and we have to do this in the same way with all the other predefined functions. So what's the semantics of arg of? Well, it's the expected semantics, arg of constr. So arg of constr also takes some object from the domain. And if this has this form here, it's built with this constructor, and then it has certain arguments, d1 to dn, then the result of this should be the tuple consisting of d1 to dn, d1 to dn in tuples n in DOM. Here I should have said where constr prime is, of course, different from constr, so they should not be the same. So this should give back the arguments if D is really built with this constructor here, so with this constr, D1 to Dn, in constructions N in DOM. And, well, this in the special case where this is a constructor of arity 1, it should not return a tuple, but it should return just this argument. So this we only do in the case where n is not 1. If n is 1, then we return just the arguments. So it's just d1 if d is constr applied to d1 in constructions 1 in DOM. And otherwise it's bottom. Otherwise. Okay, now we need the same thing for these tuple functions. This is our n tuple and the selection function. So what's the semantics of is n tuple? Well, if I apply this to some argument from the domain, then the result is true in construction 0 in DOM. If this is really a tuple of n components, so if D is some tuple d1 to dn in tuples n in DOM, and otherwise it's bottom. And finally, the selection function also does what you would expect. So what's the semantics of cell n comma I? Well, if this thing has the form up there, then it gives you back the ith component. So it gives you back di if d has the form d1 to dn in tuples n in DOM, and otherwise it's undefined. So we now added these 5 kinds of predefined functions, and now we will start translating any complex Haskell program into an equivalent simple Haskell program. And the simple Haskell program will not have any pattern matching anymore, but it may use these 5 predefined functions. And that's the goal. And well, to make life a little easier, we will not consider all features of Haskell, but we will restrict ourselves a little bit. So we will distinguish between full Haskell, and full Haskell is a superset of complex Haskell, which in turn is a superset of simple Haskell. And we will show how to get from complex Haskell automatically to simple Haskell. We will omit the step from full to complex Haskell because this would introduce several more technicalities. So what's the difference between full and complex Haskell? Well, let's define what complex Haskell means. So what is complex Haskell? Complex Haskell means we exclude certain features. So a complex Haskell program is a Haskell program without the following features. Without. So without type synonyms. I mean, type synonyms are just syntactic sugar, so that's something you really don't need. So it's something like this. You introduce abbreviations. Instead of writing list of character, you write string. Now that makes your program shorter and more readable, but it adds no extra functionality. So this is just to avoid having to treat this. So type synonyms we omit. Type classes we omit as well. That would require some more work to include them. So this we don't have. Then we don't have infix declarations. That's, of course, just syntactic sugar. So all the infix function symbols have to be converted to the corresponding prefix function symbols first. And that's, of course, easily possible syntactically. Then we have no predefined lists. That's also no real restriction, because the predefined lists just have a nice syntax, but apart from that, we can define lists ourselves, and then they do exactly the same as the predefined lists. So this is just a nice syntax that we don't have to regard here. Then the only pattern declarations that we allow are those where a variable is on the left-hand side. So without pattern declarations whose left-hand side is no variable, now that's also not a restriction really. So something like this. In Haskell you can say x, y is the tuple 2, 3. Now that we don't allow, instead you would have to declare x equals 2 and y equals 3. So that's also easily possible. So the transforming such pattern declarations into pattern declarations where you just have a variable on the left-hand side, that's no difficulty. So that's also not a severe restriction. Then we have no where, just let. So if you have local declarations with where, then you have to transform them into a local declaration with let. But again, this is easily possible. Then we have no conditional right-hand sides. Right-hand sides. What are conditional right-hand sides? Well, something like this. If you want the maximum of x and y, then if x is greater than y, it is x, and otherwise it is y. So something like this we exclude. If you want conditions, then you have to do it with if then else. Now that's of course easily possible, and indeed Haskell implementations convert this to if then else as well. So that's also not a real restriction. So no conditional right-hand sides, but we have if and we have case. And these are almost all restrictions. 1, 2, 3, 4, 5, 6, 7. And the last restriction is also just a syntactical one. I mean, a Haskell program consists of lots of declarations, and we require that these declarations are ordered in such a way that all declarations that belong to the same function follow each other. So it's not okay to have one declaration for function f, then one for g, then another one for f, then another one for g. I mean, that looks extremely ugly, and people never write something like this. And so let's just exclude it here. So all declarations for the same function must follow each other. Must follow each other. So most of this is just, we avoid some syntactic sugar. The only real restriction is this one. We excluded type classes. So unfortunately, I won't show you how to transform programs with monads or with which exploit type classes. But apart from that, all the rest is just syntactic sugar, which you can easily transform. And you could add this to the transformation, but that would make it a little longer. So this is the only real restriction that we have here. The rest are no real restrictions. Okay, so this is complex Haskell, essentially Haskell without type classes and without some syntactic sugar. And the question is how to transform any complex Haskell program into an equivalent simple Haskell program. And the main goal of the transformation, of course, is to get rid of pattern matching. So the transformation will be done by a set of transformation rules, and the whole transformation contains 12 transformation rules, and I will present 9 of them to you here, and I will omit the remaining 3. So the transformation works by 12 rules, and here we only present the rules 1 to 9. Rules 1 to 9. And the main goal of these rules is to remove pattern matching. The main goal of the rules is remove pattern matching. And the nice thing of this transformation is that it works automatically, so you can implement this transformation. And for that reason, we will use it not only to define the semantics, but we will also use it for implementing Haskell and for type checking Haskell. So whenever you have a Haskell program, you can first transform it automatically into an equivalent simple Haskell program, and then implement this simple Haskell program or type check the simple Haskell program. And in this way, we have also implemented the complex Haskell program. So that's the idea. And, well, how do we do this? We have to remove pattern matching. Yeah, and we also have to obtain just one single declaration. One single declaration of the form that is allowed in simple Haskell, var equals exp. Because in simple Haskell, the program consists just of a single equation, and on the left-hand side of the equation, there's just a variable and nothing else. So let's do this, and I will introduce these rules in parallel to an example which illustrates them. And the example that I want to illustrate them with is the append program. So how would you write append in Haskell? If you have complex Haskell, you would probably write it like this. So this is append on the predefined lists. And the goal of append is you take 2 lists and concatenate them. So this looks natural. This is the way you would most likely write it. If you want to append the empty list with another list z, the result is z. And if you want to append a non-empty list like this with another list z, well, this is the list that starts with x, and the remainder of the list is y. So the resulting list will also start with x. So the result is cons x. And now we call append recursively on the rest list y and on the second argument z. So this is the natural implementation of append, but it's not simple Haskell. Why? Well, because you have 2 equations, and in simple Haskell you may only have 1 equation, and the equation may only have a variable on the left-hand side. And moreover, we use pattern matching here. I mean, here we match with the pattern nil and with the pattern cons, and that's not allowed. So how do we transform this? And okay, before I start doing this, I will wipe the board. Okay, so the first thing that is not allowed in simple Haskell is that we have several defining equations, and then we have something else than a variable on the left-hand side. So how could we modify this? Well, one way of modifying is we have to replace this by just a single defining equation that does the same thing, and where we have only the variable append on the left-hand side. And the first rule does exactly this. So the first rule, the first transformation rule that we introduce, transforms a sequence of function declaration into one single pattern declaration. So let me write this down. So this is rule number 1. And rule number 1 is transform sequence of function declarations into one single pattern declaration. A sequence of function declarations into a pattern declaration So how does that work? And these rules are written in the following form. I will write down the original form of the expression that we had before, and then I do a big horizontal bar, and then below the bar I write down the result of the transformation. So suppose you have a sequence of function declarations that looks like this. So here var is the name of the function, and in the first declaration it is applied to pattern 1, 1 until pattern n1, and the result here is x1. And then we have many such declarations for the same variable. So the last one has this form, var of pattern 1k to pattern nk equals xk. So these are k declarations for this function var, and this rule replaces them all by one single declaration, namely the single declaration that looks like this, var equals something. Now, I have to bring all this declaration to the right-hand side. How can I do this? If I want var on its own on the left-hand side, then on the right-hand side I should write a lambda expression, because var should be a function that takes n arguments. So it should be a function that takes n arguments, x1 to xn. And now what should happen next? Well, pattern matching should happen. So we should find out whether this tuple of patterns, pet11 to pet n1, matches the actual arguments. And for this we can use the case construct in Haskell. So if these actual arguments, x1 to xn, if they are matched by the tuple of patterns pattern 1, 1 to pattern n1, then the result should be x1. Otherwise, we check whether pattern 1, 2 to pattern n2 matches these arguments, and then the result would be x2. And then finally, we check whether the actual arguments are matched by these patterns. So by pattern 1k to pattern nk. If they match, then the result is xk. And this is equivalent to the sequence of function declarations above, where x1 to xn are fresh variables, n is greater than 0, so we don't do this if this is not really a function taking arguments. And this sequence is maximal. So these are really all the function declarations for this function var. And the sequence of function declarations for var is maximal. So after that, there comes no function declaration for var anymore, but something else. And also before, there is no declaration for var, but something else. And the sequence of function declarations for var above is maximal. So these are all the function declarations for this function. Let's do this in our example and see what we get. So instead of having these two declarations, we want a single declaration with just append on the left-hand side. So what would rule 1 do? It would replace this declaration by the new declaration down here. So now we have just append on the left-hand side. And append now is a function with two arguments, because we had two patterns here. So lambda x1, lambda x2. And then we have a case construct. And now we have to find out which of the patterns here will match these actual arguments. So here are the actual arguments, x1 and x2, and the question is which pattern matches them. If they are matched by the first pattern, by nil z, then the result is z. So if they are matched by nil z, then the result is z. If they are matched by cons x, y, and z, then the result is this term over here. So if they are matched by cons x, y, and z, then the result is this term over here. So by applying this rule in our example, I have transformed this original sequence of two function declarations into a single pattern declaration with a variable on the left-hand side. So that's already good, but we are not yet there because this is not yet simple Haskell, because in simple Haskell the case construct is not allowed, because case does pattern matching. I mean, case does pattern matching. The question is, does this pattern match this argument? And if yes, this is the result. And otherwise we check whether this pattern matches this argument. And so this has to be removed. So this will be the goal now. Now the first thing that is not allowed are these lambda abstractions with more than one variable. So lambda abstractions, in simple Haskell you may only have lambda abstractions with one variable, but not with many variables. Now to get rid of this, that's rather easy. So how can we solve this problem that here we have several variables, but only one variable is allowed? This is done by rule number 2. So this does transform lambda abstractions with several patterns. With several patterns. So there should only be one pattern and not many. Several patterns. So if you have a lambda abstraction like this, you first wait for pattern 1, and you wait for pattern 2, and you wait for pattern n. And this is mapped to some expression x. So this is a function taking n arguments. The first one must be matched by pattern 1, and the last one must be matched by pattern n. And then this is the result. Instead of having this, we can replace this by a simple Haskell expression, well, an expression where we only take one pattern at a time, namely it's the lambda expression where we take pattern 1, and then the result is the lambda abstraction where we take pattern 2, and so on. And finally, we have the lambda abstraction where we take pattern n. And this is clearly equivalent, and of course we only do this if n is greater or equal to 2. So in this way, we solve the problem that in simple Haskell only one argument is allowed after the lambda. So if we do this in our example, then, well, instead of lambda x1, x2, we now have two nested lambdas. And the rest remains the same. So what's the next problem? Well, in general, another problem is that here, after the lambda, we may have an arbitrary pattern, but that's not allowed in simple Haskell. In simple Haskell, you may only have a variable after the lambda. Now, in our example, that doesn't happen because x1 and x2 are already variables, but in general, this could happen. So let's introduce a rule also which gets rid of patterns after the lambda. So the next rule, which is not applicable in our example, but what would happen if this were really a pattern? So transform lambda abstractions which have patterns instead of variables. So if you really have something like this, lambda pat exp, and pattern, and this pat is no variable, where pat is no variable, then the idea is, I mean, we have to get rid of pattern matching, but let's first transform all occurrences of pattern matching into case constructs, and then we discuss how to get rid of case. So we could transform this pattern matching under the lambda into a pattern matching with case. So we could say, well, this is the function that takes an arbitrary variable And now we check whether the argument here is matched by this pattern. And we can do this by a case construct. So we could say, if this variable is matched by this pattern, then the result is exp. And this does the same thing. I mean, that's the semantics of case. If this pattern matches this variable, then everything works well, and the result is exp. So var should be a fresh variable. And var is a fresh variable. Okay, so now the remaining problem is how to get rid of case constructs, because case constructs do pattern matching. And now this case is not so easy to read, because somehow we first write the argument, then we write the patterns, and then we write the results. So to make the formulation of the remaining rules easier, I will translate these case constructs into an equivalent construct, but which makes the rest easier to read. So what I will do is I will introduce a new construct which is not part of Haskell and is just used as an intermediate step. And this new construct we will eliminate afterwards again. So this is just used as an intermediate step in the transformation. So to ease the remaining transformation, we transform case constructs into constructs with a special keyword match. And these match constructs will be eliminated again afterwards. So they are really just used as an intermediate step. So we introduce a match construct which will then be eliminated again during the transformation. So this is just used as an intermediate step. And what does this match construct do? So this match construct is used to express pattern matching. So match takes 4 arguments, a pattern, and three expressions, x1, x1, and x2. And what is the meaning? The meaning is we want to match this pattern against this expression. If this works, then the result is x1, and if this does not work, then the result is x2. So this means the following. We match this pattern against the expression exp. And if this succeeds, then the result is x1 with the variable instantiation that has been computed during this matching. If this succeeds with some matcher sigma, so sigma instantiates the variables in this pattern in some way, then the result is x1, where the variables in x1 are also instantiated by this matcher. Then the result is sigma x1. And if this does not succeed, then the result is x2. Otherwise, the result is x2. So we can translate case expressions into match expressions now, and well, with this, the formulation of the remaining rules gets easier. So let's do it. How can we transform a case expression into a match expression? It would be nice if we could read this. So this is done by the next rule. This is rule number 4. And this transforms case expressions to match expressions. Transform case to match. So if I have a case expression like this, if this expression is matched by pattern 1, then the result is exp1. Otherwise, if it's matched by pattern 2, then the result is exp2. And finally, if this is matched by pattern n, then the result is expn. Instead of writing this, I could also write the following expression that uses match. So what do I have to do here? I first have to find out whether pattern 1 matches this expression. So I match pattern 1 against this expression exp. And if this works, then the result is exp1. And if this doesn't work, then I match pattern 2 against this expression. So the last argument of this match is this new match expression where I match the pattern 2 against exp. And if this works, the result is exp2. And if this doesn't work, then I match pattern 3 against this expression and so on. And finally, in the end, I match pattern n against the expression exp. And if this works, then the result is expn. And if this doesn't work, then the result is bot. So instead of writing case, I can also use these nested match expressions. And now what remains to be done is I have to get rid of these match expressions. Now let's do this in our example. So if I translate case to match in our example, how would it look like? It would look like this. So what did I change? Let's see. So this case construct, what did I do here? Here I have to match nil z against x1, x2. So I have to match nil z against x1, x2. If this works, then the result is z. So if this works, then the result is z. Otherwise, I have to do the next matching. So I have to match cons x, y, z against x1, x2. So I have to do this matching of cons x, y, z against x1, x2. If this works, then the result is this term over here, this cons term. And if it doesn't work, the result is bottom. So this is done by rule number 4. And now what remains to be done is I have to get rid of this match construct. So I have to get rid of all these pattern matching problems. And now I just consider the different forms of patterns. So how could patterns look like? Well, in this example, the patterns are tuples. So the first thing that I have to get rid of is tuple patterns. This is a pattern consisting of a tuple of 2 patterns. It's the pattern nil and the pattern z. And if I build a tuple of them, it's again a new pattern. So the first thing is let's get rid of tuple patterns. How can I do this? So now eliminate the match construct. For all forms of patterns. And the first form are tuple patterns. So if I want to match a tuple pattern against some expression, so if I want to match a tuple of patterns, pattern 1 to pattern n, against some expression x, well, what do I have to do? I first have to check is this really also a tuple of n components? And if it is a tuple of n components, then I have to do this pattern matching component-wise. Then the first pattern here has to match the first component here, and the second pattern here has to match the second component there, and so on. So first, check if X is also a tuple of n components. And then do pattern matching component-wise. Component-wise. So if we do this, then we arrive at the following rule. And, well, this is not rule number 5, but it's rule number 9. Because for some reason, the rules were numbered in a different way than I introduced them here. So this will be rule number 9. Rule number 5 will come afterwards. So rule number 5 is concerned with matching of tuple patterns. So I have a tuple pattern, pattern 1 to pattern n, and I want to match this against this expression, and if this works, the result is x1, and if it doesn't work, the result is x2. And now the question is, how can I replace this by match constructs that do not work on such a tuple? Well, we've just thought about it, and we found out we first have to check whether this is really a tuple of n components. And we can do this by one of our predefined functions. That's why we have this function is a n tuple. So we now check if this is really a tuple of n components. So if this is really a tuple of n components, then we do matching component-wise. So then we match pattern 1 against the first component of this tuple. So we match pattern 1 against the first component of this tuple. And how do I get it? I get it by this selection function. So I take this n tuple and I select the first component. So cell n1 exp gives me the first component here. And if this works, then I can continue and match the second pattern, pattern 2, against the second component, cell n2, of this expression, and so on. And now I have the problem that this doesn't really fit. So I do this for all the patterns, and then finally I match pattern n against the nth component, cell nn of exp. And if this doesn't, and if this works, then the result finally will be x1. So this is the first argument of this match. This is the second argument. The third argument should be x1. And if it doesn't work, so all these pattern matchings work, the first component matched, the second matches, but the last one, here pattern matching fails, then the whole pattern matching fails, and the result should be x2. So here it should be x2. So these are the last two components, should move in here. And so this means that if all these components matched and everything worked well, we get x1. If the last one failed, we get x2. If the but last one failed, we get x2 as well. If the second one failed, we get x2 as well. And if the first one failed, we also get x2. So this looks a bit unreadable. So the problem is that there's not enough space on this blackboard, so this was badly layouted. I apologize. maybe I should, to make this more readable, let's write this on the second blackboard. So if we write this below this, then this pattern, this match application has x2 as its last argument, and this match application also has x2 as its last result. So if this was an n-tuple, then we do all these matchings, and if one of the matchings goes wrong, we have x2 as the result, and if all the matchings work, we have x1 as the result. And what happens if this x was no n-tuple? Well, then we return bot. No, then we don't return bot, but then the whole matching does not work, then we return x2 as well. So this means we first check whether x is an n-tuple. If so, we do component-wise matching. And if all these matchings work out, we get x1. If one of these matchings fails, we get x2. This is if the last matching fails. This is if the second matching had failed. This is if the first component didn't match. And if this whole thing was no n-tuple, then we also get x2. So let's do this in our example. How would it look like in our example? So before we had this version of the append program, and now we want to get rid of these matchings. And of course, this will look a bit horrible, but we will simplify this afterwards again. So if we apply this rule, we get this ugly looking construct. And how did this happen? Well, for example, if we look at this first match expression, here we first have to find out whether x1, x2 is an n-tuple, a tuple of two components. And to make this a bit more readable, I omitted this already on the slide. So otherwise it would look even more horrible. So on the slide, I omitted already if expressions that are obviously true. So expressions like this, if is an n-tuple, if this was applied to an expression that already consisted of n components, then x1 else x2. Yeah, we replaced such expressions by just writing x1. Should we call this? So if I had an expression like this, where I applied is an n-tuple to something which already consisted of n components, then I evaluated this to true immediately and replaced this whole if-then-else expression by exp. And that's how I arrived at this ugly-looking construct. So I know already that x1, x2 is a component, is a tuple of two components, and so now I do component-wise pattern matching. So nil was matched against the first component of this tuple, and z was matched against the second component of this tuple. And if this works, then the result is this thing, it's z. And if it doesn't work, then I have to look at the alternative where I have to match cons x, y, z against x1, x2. And if this works, then I arrive somewhere here. And if this doesn't work, if matching fails somewhere, I get bot, because the last argument over here was bot. So by application of this rule, I get this ugly-looking construct. And now to simplify this a bit on the slide, I will do some simplification. So instead of writing cell 2, 1 of a tuple like this, I will simply write x1, because the first component of this is obviously x1. And the second component of this is x2. And similarly here and here and here and so on. So to make this a bit more readable on the slide, let me do this simplification, because otherwise we will have problems reading this. So if I do this simplification, then I get the following. Okay. Okay, so now with this simplification, it looks like this. And that's something we can at least look at without hurting our eyes too much. Okay, now we have to remove the remaining occurrences of match. Now here, we know again what match means. Match means I want to match this pattern against this expression, and if it works, I get this exp1 back. Now some of these matches clearly work. As soon as we match a variable, so here we match a variable against some expression, and matching of variables always succeeds. So z, if I match z against x2, I know that this will work, and what will happen, I will instantiate z by x2. And therefore the next rule treats the case where the pattern that I look at is a variable. So now it's not a tuple of patterns, now it's a variable. So this is the next rule, this is rule number 5. But to write it down, I need more space. So rule number 5 is matching of variables. So if I have an expression like this, I want to match a variable against some expression. And if this works, then the result is exp1. And if it doesn't work, then the result is exp2. This I can simplify because I know that this always works. So the result here is always exp1. But all occurrences of this variable in exp1, they have to be instantiated by exp. And now to express this, I can use a lambda expression. So I can just write this. And what does this mean? This is the function that maps var to exp1. And it's applied to exp. So this means that this is like exp1, but all occurrences of var are instantiated by exp. By exp. And this is what's happening when I match a variable against an expression. So if I do this in our example, then this means that here I match z against x2. So the result is, and then the result is z. So the result is like z, but all occurrences of z are replaced by x2. So this z is the z over here, but all occurrences of this z here are replaced by x2 here. And similarly here, this matching will also always work. So the result is this const term, but all occurrences of z are replaced by x2. So it's this const term, but all occurrences of z are replaced by x2. So that's the idea of these of this rule number 5. And well, to make this a bit more readable, I again did a little simplification. So instead of writing this lambda term here, I just write x2, and instead of writing this, I just write cons x app y x2. If I do this, then I get this down here. So here I have these lambda terms, but this in fact is x2, and this in fact is cons x append y x2. So by applying this rule, I can get rid of matchings where I match a variable. So now I explained what to do if I match tuples of patterns and what happens if I match a variable. Now what other patterns do we have? Another possible pattern is the joker pattern, and that of course also always works. So if I have the joker pattern, the rule works in the same way as for variables. So match of the joker pattern this works in the same way. So if I match the joker pattern against some expression, and then the result is x1, and if it doesn't work, the result is x2, then I know this always works, so the result of this will always be x1. Now, what's next? I mean, in this example, the joker pattern doesn't occur, so this I cannot illustrate. But the next thing is the matching of constructors. So this will be the next rule. You see that we have almost made it, so just 2 more rules. So what happens if I match? This is rule number 7. When I match constructors. Match of constructors. So what happens if my pattern starts with a constructor? So it looks like this. Here I have a constructor applied to n patterns. And if this matches my expression x, then the result should be x1. Otherwise, the result should be x2. Now, when does this work? This works if this expression is built with the same constructor. And how can I find this out? Well, it works in a similar way as with the tuple. So I used the predefined is a function to check whether this expression really starts with this constructor. So I could check whether this expression really starts with this constructor. And if so, then what do I have to do? Well, then these arguments here have to match the arguments of the constructor here. So then I call match again, but this time with the tuple of argument patterns, pattern 1 to pattern n. And they have to match the arguments of the constructor here. And now I use this predefined arg of function to get the arguments of the constructor. So arg of constr of x. And if this works, the result will be x1. And if it doesn't work, the result is x2. And if this is not built with this constructor, then the matching fails for sure, and the result will be x2. So this is how pattern matching works for objects built with data constructors. So let's look at our example to see what's happening here. So this is the way that the append program looked like. And now I have to apply this rule number 7, because here nil has to be matched against x1 and cons xy has to be matched against xy. Okay, and the result looks again a bit ugly. But I mean, this transformation is meant, it's compiling. So this is the compiler from complex to simple Haskell, and clearly a compiler is something that a machine should do, so if it looks ugly, that's no problem for the machine. So what do we have to do? We have to match nil against x1. So we have to check whether x1 was built with nil. And if so, then we have to match the arguments of nil, which is the empty tuple, against the arguments in the actual object x1. And if this doesn't work, we do the same thing with cons. So we have to check whether x1 was built with cons. And if so, then we have to match the arguments here, so xy, against the arguments of x1. So we match xy against the arguments of x1. And if this all works, we get this result. And if the matching goes wrong somewhere, then we get bot. So this is this rule number 7. And well, now again, we can simplify this further. We now have again a matching of tuples. How to deal with tuples, we know already by rule number 9. And in this way, we can finally simplify the whole thing. The only thing I didn't explain yet is how to match the empty tuple. So what happens if we match the empty tuple? In this rule number 9, we matched a tuple that was not empty. So if we want to match the empty tuple, that can be done as well. And this is the last rule that we need. So the matching of the empty tuple. Well, here, if we want to match the empty tuple against some expression exp, and if this works, the result is x1, and otherwise it's x2. Well, here we simply check, is exp the empty tuple? And if yes, the result is x1, and if no, then the result is x2. So we have this function is a zero tuple. We check whether exp is really the empty tuple, and if yes, we get x1, and if no, we get x2. And if we apply all of this and do some simplifications afterwards, then we finally arrive at the final version of our append program, and that looks like this. So at the very end, we get this result. And this is indeed somewhat understandable again. And now this is simple Haskell. So append is a function that takes two lists, x1 and x2. We check whether the first one is nil. And if yes, the result is x2. Otherwise, we check whether the first one was built with cons. And if yes, then the result is cons. And now we take the arguments of cons, which is a pair of two arguments. We select the first one, and that's the first element in this list. And we call append recursively, and this is the rest of the list. So we take the arguments of cons, select the second of them, so this is the rest of the list, and append this with x2. And if something goes wrong, the result is bot. So this is the version of append without pattern matching. And what was this all good for? Well, this was good for the following. We can now define the semantics also of complex Haskell. So what we say is we introduce the following definition and say that we can transform every complex Haskell expression exp into an expression xtr, and this is just done by the rules. So I presented to you the rules 1 to 9, and there are 3 more rules in order to handle also programs with several function definitions. So in our program, we had just one function, namely append. And what happens if your program contains several functions, maybe not only append, but also length and, well, any other functions? So if you want to handle programs with several functions, then some more rules are needed. But you can now imagine that something in a similar way is also possible for larger programs. And this way, you can transform any complex Haskell expression into a simple Haskell expression, which I just denote by adding tr in the subscript. And we say that, well, xtr is defined as the result of transforming exp with these rules 1 to 12. And one can prove that these rules are really terminating and give you a unique result. So you can really apply these rules, and then you get a unique result. And then one can finally define the semantics of complex Haskell in the following way. Okay, so the final definition is the semantics of complex Haskell It's as follows: for a complex Haskell expression exp, we can now define its semantics as follows. It's defined as follows. Well, what we do is we do it almost in the same way as we did it for simple Haskell. Oh, exp in a Haskell program P, in a complex Haskell program P. So if we want to find out its semantics, then we make this program P local. So we say, instead of regarding this expression in this program, we regard the following let expression, let P in exp in the empty program. So we now just consider the semantics of this. So we consider the semantics of this. but of course, this val function was only defined for simple Haskell and not for complex Haskell. So what do? This is a complex Haskell expression. We transform it. So we take this expression and use this transformation. And this transformation just means apply these rules until you cannot continue anymore. So these rules give you a unique result, and their application is terminating. So if you apply these rules, you will transform this complex Haskell expression into a simple Haskell expression. And now we are interested in the semantics of the simple Haskell expression. And in which environment do we do this? Well, not in the initial environment of ordinary Haskell, but we also have to consider the semantics of these additional predefined functions. So all these predefined functions, well, their semantics has to be known as well. And so we take this simple Haskell expression in this environment, and this is defined to be the semantics of this complex Haskell expression in the complex Haskell program. Okay, and this transformation, well, since this works automatically, you can apply these rules automatically. You can use this not only to define the semantics, but you can also use this for implementing Haskell or type checking Haskell. And so in the remainder of the lecture, we only have to look at simple Haskell, and we know that everything we do for simple Haskell can also be used for complex Haskell because it can be compiled to simple Haskell. Okay, so see you again on Friday, and on Wednesday there's an exercise course as usual.